Today I'm going to be talking about superconducting nanowire single photon detectors. These are very long and narrow nanowire structures that, just to give you an idea, can have cross-sectional areas on the order of a couple hundred nanometers, but usually have lengths on the order of tens to hundreds of microns. And in this video, at a high level, I'm going to go over some of the basic operating principles behind this device, and I'm going to show how we can create a basic model for how the device operates using just some basic RL circuits. Okay, so what we're going to do first is we're going to bias our device with some bias current that's below the critical threshold to ensure that we are keeping the superconducting state. And essentially, what we're going to do is make our device such that a single photon can disrupt the superconducting state. And what that's going to allow us to see is when this photon is absorbed, the material is going to absorb some of its energy and it's going to create a local hotspot where this single photon is going to have enough energy to temporarily break the superconducting state locally, creating a small resistive barrier. Now, when we have this small resistive barrier, what that means is that when current is flowing through some portion that has some finite resistance, we can measure voltage across it. So eventually what we're going to see is we can detect photons as voltage pulses at the output. And once this resistive barrier has created, the energy is going to start dissipating and it's going to start cooling back down, right? Because we are still cooling this so that it maintains that superconductivity globally. And this is just a local change in its superconductivity. So what's going to eventually happen is the superconductivity is going to get recovered, right? Because the device that we're using to cool the material is just going to cool it back down. And there's two time constants associated to this process. One is how long does it take from photon absorption to the creation of this local resistive barrier? That's going to be some time constant. And then the more important one is what is the time constant associated with going from a photon detection where we find the voltage pulse to returning back to this detection state where we are ready for another photon to be detected. Before we talk about those time constants and modeling it as an RL circuit, let's talk about some of the implications of superconducting materials. So for superconducting materials, what we see is that below some critical temperature, we get a drop to zero electrical resistivity. So what that means is that we have no electrical resistance. So current can just flow freely and is unimpeded by anything. And another thing is at low temperatures, we're dealing with very, very small amounts of thermal energy, ideally no thermal energy. So we have negligible lattice vibrations. So normally, even at room temperature, the lattice in our material is vibrating like crazy and it doesn't really interact with the charge carriers that we're dealing with. But at really low temperatures, there's not that much thermal energy. So the lattice is not really vibrating very much, and the interaction with the charge particles is actually going to be important. We're going to talk about that when we talk about Cooper pairs, which is also on this list. And we're going to talk about this concept of kinetic inductance, which is essentially coming around because the charged particles store kinetic energy in them. So when we change the current, that's going to change their acceleration. That's going to change the acceleration of the charged particles. And because these charged particles have mass, there's going to be some inertia. There's going to be some physical property that's going to resist this change in motion. And that's going to be modeled with some inductance, which we'll talk about when we do our circuit. And the last thing is this idea of Bose-Einstein condensation, which we will discuss on the next slide. So on the left, I show this image talking about Cooper pairs. This is a very basic demonstration of how you can think about Cooper pairs, where what happens is because of these really low amounts of energy and the lattice is not vibrating very much, the lattice can actually be distorted by the Coulombic force based on the electron, right? So as the electron moves through the lattice, it actually can distort the positively charged ions in the lattice. And what happens as a result of that is it pulls them in and it creates these regions where the positive charge density is a little bit higher, which can attract another electron. And we get this formation of electrons moving through the lattice very easily, having almost no scattering events, giving rise to the zero electrical resistance. And what I wrote above here is that electrons are fermions, which means that they are modeled by Fermi-Dirac statistics. They obey the Pauli exclusion principle, where no two fermions can exist in the exact same quantum state. But in this scenario, when they are in a Cooper pair, they effectively have zero spin as a group, making it something that follows Bose-Einstein statistics. So it's a boson. And one of the things about this formulation is that bosons can occupy the same state, leading to this macroscopic wave function psi that describes the superconducting condensate. So it's energetically favorable for these electrons to all occupy this superconducting ground state. And here on the right, there's this energy band diagram of this superconducting gap, where it shows that there is some energy needed to break these Cooper pairs that are just sitting in this superconducting ground state. And it takes 2 delta. Delta is the energy it takes to break off one electron, to excite one electron from this ground state to this excited state. But since Cooper pairs need to exist together, it needs 2 times that delta energy to excite both of them into this quasi-particle state, or this excited state. And if enough Cooper pairs are excited up to this quasi-particle state, then what happens is that this wave function collapses. And what we'll see in our device is that when we get a photon incident on our device, it's going to create a local hotspot where it creates a resistive barrier, and it breaks this superconducting state locally before it cools back down again. So now we can talk about how we can model this as a circuit, and we have some example values here. So as we discussed in this slide, we're going to be biasing it with some current. So in our circuit representation, we are going to want some bias current. And we discussed that when it's in its detection state, when it's just waiting for a photon to arrive in this state, the current is just flowing freely and there's no electrical resistance. So we can model that as a switch that goes between 2 states, the detection state and then the absorption state, we can call it, when it actually detects a photon. But what we'll see here is in its current state, this is in the detection state, current is going to just flow freely. And when it gets here, it's going to face 2 paths. It's going to face some small 50 ohm resistance, or it's going to take this path where we have an inductor, but no resistance. So essentially what's going to happen is that in this first detection state, current is just going to just flow freely, and there's no electrical resistance, no current will want to go through here, so it'll just keep flowing through this loop. But when we have a photon detection, it's going to break the superconducting state, and as we discussed, there's going to be some resistive barrier. And what that means is that in terms of our circuit diagram, it means that this switch is going to close. So now this will be open. And now the path that we need to consider is this current will flow through here, and it'll have a choice of going through this 50 ohm resistor or through this path where we have some comparably very, very large resistance to this small 50 ohm resistor. So essentially all of the current is going to flow through this part of the circuit here. And ultimately what we're going to measure is the voltage drop across this 50 ohm resistor, right? So that's the idea. And this circuit should make a little bit of sense based on what we talked about, right? Because from the beginning we said we're going to have a bias current and things are just going to flow freely. So in that state, there's going to be no voltage drop across this resistor because there's no current. In the detection state, there will not be any voltage drop. But we want to model this in such a way that when we do detect a photon, when we do have a resistive barrier, which is modeled by this 3 mega ohm resistor, we want there to be a voltage reading across this, which there will be. There will be. Most of the bias current is going to flow through this path because it's going to have a low resistance. So we will measure some voltage pulse. And this is really interesting because now we have some example values. We have our bias current. We have this resistance that's found experimentally that has this relationship between the bias current and then the output voltage pulse. But ultimately what we want to see here is in the detection state, we just see our bias current, no voltage output reading. And once we've created this resistive barrier, that's like the second switch in the circuit, we have a voltage reading across our output, meaning we have detected a photon. And what we can do is we can analyze these two circuits and find their associated time constants. And just to give an example with these values, I won't go through the analysis, but we can look at the results. And what we'll see is the most important part that we want to see is we want to get an idea of the order of magnitude of these time constants. So if we calculate the time constant in the first circuit as it's shown here in the detection state, we have a delay from superconducting to the resistive state of about 50 picoseconds. So what that means is from going from a photon being absorbed to creating this resistive barrier, breaking down the superconducting state, it's somewhere on the order of 10 to the minus 12 seconds. So it's very, very small. And then if we analyze the next part of the circuit, going from the resistive barrier back to the detection or the superconducting state, that time constant is a little more important because that will tell us a little bit about the frequency at which we can detect photons. It tells us like the reset time of the device, essentially. And if we go back to here, what we see is that the time constant is larger, but it's still pretty small. It's on the order of nanoseconds. And based off of the numbers that we had here, we find that this device would have a count rate frequency of about 100 megahertz, which is pretty dang good. And we know now from doing research that the state-of-the-art devices can go up to 6 gigahertz. So I hope that this video was interesting and you learned something from it. This was just a little high-level overview of this pretty cool device that is used in optics, quantum photonics, and many other fields. And much research is being done to find devices that work under the same basic operational principle, but can have different applications because there's a lot of trade-offs as far as what wavelengths these devices can detect, because depending on the frequency of the photon, the incident photon, it's going to affect how much energy it gives the system. And we need to design our devices with that in mind. And there's also this challenge of fabrication where if we have devices that can be fabricated to be a little bit larger, we can use optical lithography instead of electron lithography, which will make it a lot more accessible and a lot cheaper. So there's a lot of research being done to find these trade-offs as far as fabrication and making detectors that can work with the research that you need, right? If you're studying light at a certain frequency, you want to have a device that can detect efficiently at that frequency. But there's all these trade-offs that you need to keep in mind. So this is still an active field of research, and there's a lot of work to be done, but hopefully this is a cool high-level overview of this device.